So this time around we have this problem. A man stands on the roof of a building 50 meters high and throws a rock with a speed of 60 meters per second at an angle of 37 degrees above the horizontal. Calculate the maximum height above the roof reached by the rock, magnitude of the downward velocity of the rock, horizontal distance from the base of the building to the point where the rock strikes the ground. First thing is to picture the problem, so we're going to create a rough diagram to show us what is happening here. We'll place our ground somewhere here. So this will act as our ground. And then we'll place our building something like this. Okay, it doesn't have to be perfect, but let's say this is our building. So this man throws that rock and throws it at an angle 37 degrees above the horizontal. So if the horizontal is something like this, 37 degrees above the horizontal, so let's say this object is thrown with a velocity like this, the velocity 60 meters per second. Angle to the horizontal, 37 degrees. We know to say when projected, the trajectory that will be followed by this rock is going to be parabolic. And since this is being thrown from the building, it gets to land somewhere below or on the ground. So it gets to go up, then gets to come down and land somewhere there. So this shows the trajectory that rock is going to follow. In the first part, they're saying calculate the maximum height reached by the rock. So the maximum height above the roof. So follow the language and how they are phrasing it there. They can say above the ground. Above the ground would have to be from here all the way up to the maximum height. That would be the maximum height reached above the ground. But in this case, they're asking for the maximum height above the roof. The roof is here, so maximum height above the roof would have to be just this part here. So that is what we're going to go for. So if we're just looking for above the roof, meaning we're starting from the roof, going up to the maximum height. So what do we know? This is all happening in the y-axis. What is the initial velocity in the y-axis? If this is projected with a velocity of 60 meters per second, 37 degrees above the horizontal component to be given by cosine 60 cos 37, and the vertical component to be given by sine. So it will be 60 sine 37. From here, the initial velocity in the y, we've just seen it to be 60 sine 37 degrees. But since we are going to the turning point, to the maximum height, the final velocity at the maximum height will be 0. When the y-axis, where acceleration is present, and it's always downwards, 9.8 with a negative, and we're looking for the maximum height reached, meaning we're looking for the displacement up to the maximum height. So that's an upward displacement, S, we'll just label it as H. So here, of course, you see that you don't have time, so pick the equation that doesn't have time. U squared plus 2as. When you substitute, at the maximum height, final velocity is 0. Initial is 60 sine 37. We have to square it, plus 2. Acceleration, minus 9.8. Displacement is our height h. So from here, We can make h the subject of the formula, but basically we have 0 is equals to 60 sine 37 squared minus 19.6 when you multiply these. So 19.6 goes the other side, 60 sine 37. So usually you can carry this the way it is and only evaluate the last minute. That will save you from rounding off a bit too early. Then this is now over 19.6. At this stage now you can evaluate. So can you calculate this? What answer are you finding? So here we have 1.12 meters. Okay, so that comes as the maximum height above the building. So just want to be very careful when evaluating this and make sure that you don't make any mistakes. Okay, so this is 66.5 and not that 66.5 meters. So you just want to be very careful. Sometimes you can just look at the values that you have here. 60 sine, it's going to be something big. It's not going to be very small. When you square, expect it to even be bigger. Then divided by 19.6. That will give you an idea of at least what you're expecting there. All right. So we have found the maximum height. We can now look at the magnitude of the downward velocity of the rock just before it strikes the ground. So here, just pay attention to the phrasing here. They're saying the downward velocity. You see, when the rock is striking the ground, it strikes the ground here. And the velocity it has when striking the ground, it's a velocity that is in that direction. And observe that that velocity will have two components. A vertical component that goes vertically downwards, and a horizontal component that goes to the right, like that. In the question in B here, they're specifying the magnitude of the downward velocity. So they're not really asking for the overall velocity it reaches the ground with, but they're asking for the downward velocity, meaning they're looking for the final velocity in the y-axis, the velocity it will hit the ground with in the y-axis. That's the one that they're asking for here. Again, I am specifying that when a projectile is landing, it goes like this. If it is landing, at the point of landing here, we know to say it will have a velocity in the direction of motion like that. But this velocity can be seen in component form. It will have a sideways component, the one that was propelling it in the x-axis. This will be the final velocity in the x. But it will also have a downward velocity, the one in the y-axis, final velocity in the y. So when a question specifies to say find the downward velocity it lands with, they want the final velocity in the y-axis that it will land with. But if a question just says find the velocity it hits the ground with, so when they just say find the velocity it hits the ground with, they are not saying the y component, they're not saying the x component, they mean the overall velocity it will reach the ground with. And to get that one, you'd have to first find the y component, the x component, and then combine them using Pythagoras theorem. I think we'll look at something like that later on. For now, let's just find the downward velocity for our problem. So if it would take x, they would have just said find the velocity, the horizontal velocity it lands with. You've heard that? Yeah. And you have to see that in the x-axis, the velocity does not change. The velocity it has here in the x-axis will be the same everywhere. And since upon projection, the velocity in the x-axis was 60 cos 37, this velocity will be the same until when it lands. So it will be the same here, 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 it will be the same even up to when the projectile lands there. So sometimes they can even ask you to say, find the horizontal velocity of this projectile at a time t is equals to 5 seconds. They're just messing with you because they know you don't even have to calculate to find what that velocity is. It's something you're supposed to know that the x component here will be the same throughout. But if you forget that, you start calculating and wasting time there. Okay, so we can move on to part 2, the magnitude of the downward velocity. So since that's just the downward velocity, we are still in the y-axis. But this time around, we want the velocity it hits the ground with, meaning it's starting from the building here, it has to go up to the topmost point, then it has to fall down until it hits the ground. So we want the velocity it hits the ground with. The initial velocity is the velocity it started going up with. The final velocity is the velocity we're looking for, the one it hits the ground with. So are we given the displacement or the height of the building? We are given. The building has a height of 50 meters. So here is the easiest way to work out this problem. The initial velocity of this stone in the y-axis, we saw this one. It was 60 sine 37. And notice that this is an upward velocity. You see that, right? Next up, the acceleration. The acceleration here is due to gravity, and we know acceleration will always point towards the center of the earth. So, because of that, we'll give it negative 9.8. When using this approach, it's very important for you to respect vectors. So, respect what is down and what is up. But here, we will use a trick. There are actually two methods you can use to solve this question. I will show you both methods. So, the one that you will prefer, the one that you might prefer is the second method I'll show you. But I fancy this one because if you understand it here, it will be easy to use it even on complex questions later. Okay, so now look at the displacement. The displacement is the distance in a specified direction from your starting position to your end position. So when you look at the displacement is a downward displacement. Do you see that we end up down? Displacement. If let's say you start from position A, you walk 10 meters to the right, reach position B, and then you walk 12 meters backwards to reach position C. What is your displacement? The displacement is just the distance from where you started from to where you are. If you started from A and now you are at C, your displacement is just this small distance here. From A to C, your displacement will be equals to negative 2 meters. Negative to mean that you ended up actually behind the starting point. In the same way, if you started from A and you decided first to go to C, maybe this time C is 3 meters backwards, and then you decide to move from C to a point B somewhere here, such that now you have to move 20 meters. So what is your displacement? Again, your displacement is just the distance from your starting position to your ending position. You started from A, you ended at B. So how do you find the gap from A to B? Since you started from here all the way up to B, it's 20. It's easy for us to actually predict that this small part here, this must be 17. So you ended up 17 meters from A. So the displacement from A to B, it's actually just 17 meters. Do you follow now? So in the same way, when you look at our displacement for this object which has to fall, we start from here, and this point is 50 meters above the ground. But the projectile goes up to the maximum height and falls down to reach the ground. So when we look at the displacement, it's like if we compare where we started from and where we are, this stone just moved from this point and it came downwards by what margin? 50 meters. So the displacement is a downward displacement of magnitude 50. So here we're saying the displacement is negative 50 meters. Do you get that? So if you get it, here's a question to just make sure that you understand how this happens. Suppose the projectile is thrown and it goes like this. It lands at a building this side that is 20 meters tall. What will be the displacement of the building here? Not the building. What will be the displacement of the projectile for it to land? It's going to be what? Huh? So you have to see that the displacement will just have to be the distance from the starting point to the final point in the y-axis. So in the y-axis, the starting point is here, the final point is here. So the displacement, it actually just corresponds to the height of the building. The difference here is that now the displacement is a positive displacement because the object finds itself at a higher position than the starting position. In the case we are looking at, the object finds itself somewhere lower than the starting point. So here when it finds itself below the starting point, the displacement is negative. In the second case, or this example I'm showing you, where it ends up at a position higher, the displacement is positive. Do you see that? Okay. Okay, so this is what we have here. And then from here, we want to find the velocity it lands with, v. Because we are specific with the vectors, v is the velocity it lands with. And as you can see, this is a downward velocity. So we can say that this obviously will have to be a negative value. But it's okay. We're only looking for the question specified the magnitude of the downward velocity. So we just want how big it is. We have no time in these expressions, so we can just use v squared is equals to u squared plus 2as. Final velocity is what we're going for. Initial is what we launched it with in the y-axis, sine 37, plus 2, the acceleration, minus 9.8. The height, or the displacement, we saw that the displacement is negative 50. So now we just have to do this. And this is what is going to give us our answer. Okay, so here our V comes out as 47.8 meters per second. So this becomes the downward velocity that this stone is going to be hitting the ground with. Now, this is one way you could have actually found the answer. If you want another way that you could have used is simple. You could have also just used the fact that from the maximum height here, the stone had to fall straight all the way down until it hit the ground. But this time around, you could have used the initial velocity at the starting point as 0, the acceleration to be the downward negative 9.8. So the only thing you'd have needed is the height through which it had to fall. So the height through which it had to fall, you'd have been forced to add the distance from the maximum height up to the building, up to the roof of the building, plus the 50 for the height of the building. That would have given you the full downward displacement the stone is going to cover on its way down. Since here we had 66.5, you'd have needed to do 66.5 plus 50. So this would have allowed us to find what V was going to be. Let's see how this would have worked. Here would have had V squared is equals to U squared plus 2AS. So V squared would be equals to, the initial would have been 0 since we are starting just from the maximum height. So would have been working with 2 by 9.8. But the maximum, the height now, this is negative. The height, it's also downwards, the displacement. So this summation has to be negative there. So would have had negative, and then you have 66.5 plus 50. So that the negative here and the negative here will make positive. So just have 2 by 9.8 by, this is going to end up giving us, so you'd have 5 and 6 here would give us 11. 11 with a 6 here, 0.5. So now we have this is equals to the square root of 19.6 by 11.6.5. So we see that in this case, you'd still get 47.8 meters per second. So just up to you which method you'd prefer here. Otherwise, they both yield the same results. In the final part, we now have, they now want the horizontal distance from the base of the building to the point where the rock strikes the ground. So we see that to actually answer that one, we first need to know the total time of flight. So we now have to understand how long was the projectile in flight. To see how long it was in flight, we still have to work in the y-axis, and we're going to use this information we gathered here. And yeah, for the first one, so I can just get this. Okay, so I'll do the one for displacement one, the one that we used, the first method for the previous case. So here now I'll say that, okay, if it starts with an initial velocity of 60 sine 37, the one it was going up with, and I don't want to use the final velocity I'm from calculating, because what if it had a mistake? The acceleration here, we have negative 9.8. Then we have the displacement. it ends up somewhere down, and that's 50 meters below the height of the below the roof of the building. So how long did it actually take to fall through that displacement? So you don't have to worry much about it, how it happens. Somehow, it actually will account for the time it had to go up to the time it had to move from the topmost point until it lands. So just present it like that and calculate your time. So since now we're looking for time and you don't want to use final velocity, we use ut plus half at squared. Displacement, it ends up below, so we have negative 50. Starting velocity, we have 60 sine 37. And then we have t here, then plus half, negative 9.8, then t squared. Perhaps the only hiccup about this method is you would have to solve a simultaneous equation to find time. But how would it go? You'd have 50 here equals to 60 sine 37 t, then minus 4.9 t squared. From here, of course, move everything to the left side. 4.9 t squared minus 60 sine 37 t, then minus 50 is equals to 0. We see that A is 4.9, B is negative 60 sine 37, and C is equals to negative 50. Then again, we can use T is equals to negative B plus or minus the square root of B squared minus 4 AC over 2A. So here, when solving this one, you will find two values of time. One of them will not make sense. It might have a negative or it might be too small. So you will leave that one out just like that. Then you want the one that will be positive and it has to be big enough. So this is how it would go. Yeah.
Hello, I can't.
Okay, so yes, this, when you substitute A, B, and C, it will give you the value of T that is going to work here. But another method that you could have used to work out this, if you're trying to avoid dealing with the quadratic, remember, it's just getting t that we're trying to do. We need the value of t so that we can go ahead and find the range. So another approach that you could have used here, it's a little bit longer, but students tend to prefer it. So for a projectile that gets to land, first it has to go up to the maximum height. Then from there, it has to fall down until when it actually strikes the ground. So in the second approach, you can look at the time in two parts. The time for going up and the time for falling all the way to the ground. So as it was going up, what are we doing? To go up, it starts from the roof just up to the topmost point. So here, the initial, still in the y-axis, will be 60 sine 37. The final at this point will be 0. Acceleration, negative 9.8. So you find that we can use final, initial plus 80. Final is 0. Initial is 60 sine 37 minus 9.8 t. So t is just time for going up, so I'll say negative there. Is equals to 60 sine 37. So t1 is equals to 60 sine 37 over 9.8. So what will be t1 here? So here, get 9.8 seconds. Okay, so after getting T1 here, you now want to get T2, the time for falling down. So how do we do that? So as the stone,
Wait.
yeah,
Calculating. This calculator
yeah, so just be
maybe can
careful.
have 3.6.
3.6?
Yes.
Okay, yeah, 9.8 seems to be. Okay, so 3.6 seconds.
So 3 points. You said three significant figures.
Yes.
It's like that, right?
Uh-huh. Is this say 3 sig?
So 3.68.
3.68. Have you rounded off correctly?
Yes. It's 3.5.
Okay, so as the stone falls, as it falls from the topmost point, from maximum height. So from the maximum height to the ground, what do we see? So now we're just analyzing when it was falling from the maximum height to the ground, meaning the initial is now here. And at the maximum height, the velocity is 0. So on its way down, the displacement will now be the full height. And remember, it's a downward height, so it's negative. And we saw it earlier, it was 11.6.5. So I hope you remember it. We used it at some point here, the addition of those two. So negative 11.6, negative because it's a downward displacement. 11.6 because we have to, not 11.6, 116.5. It was this part here plus the 50 for this part. Okay. Other than this, we also have acceleration due to gravity, which is negative 9.8. So using these, we can find the time it took to fall all the way down to the bottom. So since again we're not interested in the final velocity, we'll use 0t plus half at squared. This time around, this works. It helps us avoid the quadratic equation since this part will be 0. So now we only have half, negative 9.8, and then t squared. And here, the negative will cancel here. We now have 2 multiplying 116.5. Then here you have 9.8 t squared. Then divide both sides by 9.8. T squared will be 2 by 116.5 divided by 9.8. Square root T2 times, just for falling down, 2 by 11.6.5 over 9.8. So here we get 4.88 seconds. So once you have the two values of time, the total time of light will be equals to the time for going up plus the time for coming down. Going up, we found, where was that? We found 3.68. So 3.68. Coming down, we found 4.88. What are we getting when we add them?
8.56.
8.56 seconds. So either approach here could have worked to give us the time. One results into a quadratic, but it is direct. No need for T1, T2 and adding. Then the other one requires us to split it into two parts and then find the times for each part. So you can use whichever you're comfortable with. But once you find the time here, you can now use the range in the formula for speed, distance over time. The range will be the distance. When you make it subject, it will be the speed. And remember, the speed here is the speed in the x-axis. So the speed in the x-axis is the x component, 60 cos 37. So this is the first time we're using the x component. And then the time is the total time of flight, which is 8.56. So what will be the answer here? Okay, so 410.2 meters. Okay, so this is our range.